Hi, today we will see the unique binary search trees 2 problem. So we are given an integer n and we need to return all the binary search trees having n nodes and values from 1 to n. Let's see how we can solve them. What we'll do is first let's break the problem. So first just let's focus on binary trees. Let's forget about binary search trees. Alright. So when n equals to 3, let's see what are all the possible binary trees we can get. So this is 1, 2, 3, 4. Yeah, these are all the binary trees that we can get when n equals to 3. That means they have 3 nodes. Okay, now let's see about it logically. So we want a binary tree. Okay, so we will have a root node, right? And we'll have a left subtree and right subtree. Okay, I mean left subtree can be null or it can have nodes. Okay, so root node will take one node, and left subtree and right subtree. What are the possible combinations? For n equals to 3, we can have 2 nodes in the left subtree, 0 nodes in the right subtree, or 1 in the left, 1 in the right, or 0 in the left, 2 in the right. Okay, any of these combinations give a tree with n equal to 3 nodes. But how do we generate left subtree with 2 nodes? Instead of viewing that as a left subtree, let's view it as a subproblem for n equals to 2 nodes. Okay, so when n equals to 2 nodes, we'll do the similar procedure. Okay, root node will take one node for the root, and for the left subtree, right subtree, it will have 1 0 or 0 1. This is the only possibility. And now for n equals to 1, we only have one possibility. You can just create a node and we'll return it. That's pretty much it. So what we've done here is, we've seen for n equals to 3, we observed that okay, these are all the possible combinations, and for the left subtree with n equals to 2, we made it into a subproblem and made a recursive call, and we got all the left subtrees with n equals to 2. So let's draw the subtrees with n equals to 2. This is one possibility and this is one possibility, right? So when we call this for left subtree with n equal to 2 and right subtree with equal to 0, we get these values. Okay, now we've just created this possibility. So for n equals to 3 and left subtree 2, we've just this is this combination and it is this combination, and right subtree is null. Okay, and similarly for right subtree 2, again this corresponds to this and this corresponds to this. So what we've done is, like, we recursively solved the problem, and once we got the subtrees, we've just attached them to the root, all the possibilities to the root, right? So let's just see one more case. For n equals to 5, we have a root will have one node. Okay, and there is one more case where we have all the possibilities, and left subtree can have 2 and right subtree can have 2. This is one of the possibilities. We have other possibilities as well. So we know for n equal to 2, the possibilities are this and this. Okay, so now what we do is, for this combination n equal to 5 and this specific combination, we'll draw the trees. So this is the root, and now let's name as n equal to 1, n equal to 2. Okay, for this, on the left side, we'll have 2 possibilities on the right. It's 1, so we'll take 1 again. Sorry, this is 1, and again for 1 on the left, we'll take 2 second possibility on the right, Okay, and again for n equal to 2 on the right, we'll take n equal to 1 on the right, and n equal to 2 on the left, we will take n equal to 2 on the right. It's just like we've iterated using loop. So for left subtree with n equal to 2, we get a list, right? And here we get a list. What we've done is, for every possible left subtree on this list, we've attached it to all the possibilities on the right subtree. So we've got 4, 2 into 2. Okay, now we've solved the problem of how to generate binary trees. Now let's get into the case of binary search trees. So we know a property of binary search tree. We know that any value on the left subtree, value of any node on the left subtree is less than root value, and root value is less than any node's value on the right subtree. Okay, this is the property that we know of. Okay, so if we know that for a binary search tree with range in 5, so we have 1, 2, 3, 4, 5. Okay, and we know that we got a binary tree with 2 nodes on the left and 2 nodes on the right. Okay, so what will be the possible value for the root? Based on this condition, what we can infer is this is an ascending up. So we have 2 nodes on the left, this will be gone for the left, 2 nodes on the right, this will be gone for the right, and this we can use for the root. Okay, now we can distribute this to the left subtree and this to the right subtree. What we've solved here is, given a range and number of nodes in the left subtree and number of nodes in the right subtree, what will be the root's value? Okay, so we've solved that problem. Now when we combine these two problems, so this is how to generate binary trees, all the possible binary trees with a given n value, and the second problem of binary search tree, how to choose the root value of a binary search tree when we know the total number of nodes in the tree and number of nodes in the left subtree and number of nodes in the right subtree. How do we choose the right value? We solved these two problems. Now let's combine these and solve the problem. So what we do is, we are given range 1 to n, right? Now when we solve the problem, what we do is, we are taking a root and generating all the possible left and right subtrees. Okay, left subtree can have n minus 1, 0, n minus 2, 1, so on, 0, n minus 1. Okay, and we know that if there are n minus 1 nodes on the left, 0 nodes on the right, from the range of 1 to n, or for generality left to right, we know that n minus 1 values starting from left will be used up by the left subtree and no values will be used up by the right subtree. So this will be the root's value. Okay, let's take another case. So we have 2, 3, 4, 5. We know that right subtree has 1 node, left subtree has 2 nodes. So from this range, 2 values will be used up by the left subtree. Okay, 1 value will be used up by the right subtree, and this will be the root value. Okay, so every time we just calculate the root value and we generate left and right subtrees, and as this is recursive, even these left and right subtrees, they will be generated with right values because we pass on the range. So while generating this left subtree with 2 nodes, we give it the range 2 to 3. So we say like we want to generate all the possible subtrees with 2 nodes, and it should be a binary tree with range 2 to 3. So we've solved this. As we are doing it recursively, we'll get all the possible binary search trees. So now let's have a look at the code. When left bound is greater than right bound, what this means. Well, I mean, it's not possible to generate a subtree, and it's a null subtree. And left bound and right bound are equal. I mean, we have just have this as range, which means I can only have one node, and this is its value. 2 will be its value. So that's what I create a new node, add it to the list, and return the list. Now, for bigger cases, what I do is first I get the node count. So if the range is this, I'm getting the number of node counts, which is this. So I have 4 nodes. I can generate 4 nodes. Okay. Out of this, for this combination, where left subtree has I nodes and right subtree has n-1 minus I nodes, what will be the root value? Okay. So from 2, 3, 4, 5. So if left subtree takes I, then this will be the root value. Starting from the left, if I give I values to the left subtree, this will be the root. So we can divide the generation of left and right subtree as from left till root minus 1, which is this. And for right subtree, from root plus 1 till the right bound, which is 5 and 5. Okay. And now I generate all the possible left and right subtrees. Okay. I get LST list, right subtree list. This is one combination, this is one combination. Okay. So 4, 5. So now for root, I generate all the possible combinations. With 1, I take 4 ones, 5 ones. This is one combination. Okay. 1 and 5. So similarly, I iterate and get all the possible combinations and add it to the result, and I return the result. This happens recursively. Okay. Yeah, alright guys, that's pretty much it.